Hi everyone, Dan Hellman here, and today I'd like to talk to you about electrostatics, uh, work and electric potential. So I'm going to dive right in here. So to start with, I wrote this paper maybe a month and a half or so ago, and just haven't had a chance to upload it onto a video yet. But let's delve in. So suppose we have a point charge Q in an electric field that has an electric field intensity E. So the force on the charge Q due to the electric field is going to be given by this equation here. Force equals QE. This is just how electric fields work. So if you have this charge Q here in this electric field, there's gonna be a force on this charge, just as this is analogous to a mass in a gravitational field. You have a mass in a gravitational field, the force on the mass is equal to mg, where g is the acceleration due to gravity, or you can say the gravitational field. So moving along here, the work applied by a force in an electric field is going to be the applied force dot product with the work that the displacement that the thing undergoes. So again, in a field, if we want to keep the charge from moving, we can apply our own force to the charge, and that's given by this equation here to counteract the force of the field on the charge. So if we apply a force through a certain differential distance, then we've done a differential amount of work by this dot product. This is a differential amount of work. That's the dW here. And so in an electric field here, the differential amount of work is going to be equal to the negative of the charge times the electric field dot product with the differential length dl. So here's a drawing. If we're pushing a charge through this differential length dl, by applying a force in an opposite direction as the field, so if the field is pointing this way, there's a force acting on the charge going this way. To counter that, we'd have to apply a force the other way. And when we do differential amount of force, when we apply this force in a way that's strong enough that it can do it goes this differential length, then the work done would be the dot product of the force with the differential length. And then when you integrate, you get this expression here. Work is the negative charge times the integral of the electric field times the differential length integrated over the whole length. This is what we call a line integral. Work is a line integral. So, and that's what I say here, in electrostatics, work is a line integral. So the work exerted on a charge in an electric field in moving the charge from an initial position to a final position is found by summing the dot products of the force due to the electric field intensity and the differential displacements traversed by the charge in that field. Basically, what I'm trying to say here is pretty straightforward. An integral is basically a summation. If you remember back to calculus, when you're first studying integrals, you don't actually start by studying integrals. You start by making curves and then finding the area under the curve by estimating, by making a bunch of rectangles under that curve. And as you sum up those rectangles, you get an estimate of what we call is the integral under the curve. To find the integral under the curve, you let the widths of those rectangles be reduced so that the width is just a differential width. And then you sum up all of the areas of those rectangles and you get the integral. So work is a line integral, which means that you're summing up here the dot products of, in this case, the electric field dot product with the differential length or differential displacement that the thing goes through when you apply a force to it. An integral is a summation. The work involved in moving a charge through an electric field is analogous to the work involved in moving a mass through a gravitational field. Very much the math lines up as this in many ways the same. So when you pick up an object off the ground, you're moving it through a gravitational field, you're doing work on the object. And when you push a charge through an electric field, you're doing work on the charge. And as that happens, you're changing, in the case of a mass, when you do work on an object, like when you lift a weight over your head, then you are changing the gravitational potential energy of that mass. The higher you lift that mass, the more gravitational potential energy is in the system and the more work that you've done. The work that you've done is going to increase the gravitational potential energy of the system. And same thing with an electric charge. In an electric field, when you move a charge through an electric field, you change its electric potential energy. And we do not particularly care about the electric potential energy of a particular charge in an electric field. What we do care about is the electric potential energy per unit charge in an electric field. And that's what voltage is. So down here, next page, voltage is basically the work done on an electric charge in an electric field divided by that charge. Or to put it another way, it's the electric potential energy per unit charge. And again, that is given by this integral here. This is the concept of voltage or electric potential. And this is only meaningful if the electric field we're discussing is a conservative field. This begs the question, what's a conservative field? When the electric field is established by electric charges and not by time varying magnetic fields, the electric field will indeed be a conservative field. That is, it's a path independent vector field. So in other words, just like, again, same thing with gravity, a mass and gravitational potential field. As you lift an object, the higher you lift it, the more gravitational potential energy that it has with respect to some reference point. And neglecting things like friction or air resistance or any other ways where you might experience some kind of energy losses, the gravitational field is also a conservative field, meaning that it's path independent. So whether you bring an object to the right and then to the left and then lift it up 10 feet, the gravitational potential energy is going to be a function of the height above the datum or the reference point. So a vector field is a conservative vector field if and only if it is the gradient of some scalar potential function. And we're going to talk a little bit about what a scalar potential function is. If there exists some scalar potential function whose gradient is equal to the electric field we are discussing, then the electric field is a conservative field. But at this point, we should talk about what I mean when I use the concept of gradient. The gradient of a scalar potential function at a particular position is the direction and rate of the steepest ascent at that position. So we're going to use an example of climbing a mountain. And if you've ever climbed a mountain and had a map to navigate, to help you navigate your way up the mountain, then you'll probably be familiar with the idea of contour maps or contours. So here is a contour. I'm going to try to blow this up a little bit so that you could see it better. Bear with me for 1 second. Then move some things around. And I'll even zoom in just a little more. Just 1 minute. So this is a contour map, incidentally, of one of my favorite places in the world, Mount Marcy up in the Adirondacks. I've climbed Mount Marcy many times. I love it. It's the highest peak in New York State. If you've never climbed Mount Marcy, I encourage you to if you get the chance to go. It's a tough hike. You got to be in shape to do it, but it's a glorious hike. Anyway, and you see all these contours here. You see close to the summit here, we're at over 1,600 meters above sea level. And down here, you're at like 1,400 meters, here 1,370, here 1,110, over here 1,080. So we have all these different contours. So the gradient of a scalar potential function at a particular position is the direction and rate of the steepest ascent at that position. When climbing a mountain, the gravitational potential energy per unit mass is a scalar potential function. On a map, we can see these equipotential contours. Each contour represents gravitational potential energy per unit mass, which is directly proportional to the elevation above sea level, choosing sea level for our datum or our reference point. So here's a topographical contour map. So in any particular location on the mountain, the gradient is the direction of the rate of steepest ascent in terms of elevation meters per horizontal meters. It should be fairly intuitive to see that the gradient at any particular position will be perpendicular to the equipotential contour at that point. If you're hiking in the direction of the gradient, you'll be hiking in the direction of steepest ascent. If you're hiking along an equipotential contour, your gravitational potential energy will not change, except as you lose weight or gain weight. So follow me here. If we're here at this point, we're at 1,370 meters above sea level. And if we hike kind of along this ridge, staying at the same equipotential contour, then that's not hiking along the gradient. That's not, we're not going to be changing elevation. Okay. If we hike perpendicular to the contour in the direction of steepest ascent, then that is the direction of the gradient. So we get into something called a directional derivative, and we get into the gradient. The direction of the gradient is going to be the direction of steepest ascent, and the magnitude of the gradient is going to be the rate of steepest ascent. So some important concepts there that has application not just here, but also in electrostatics. So in mathematical terms, the gradient is given by this del operator next to this scalar potential function. Now this is a scalar potential function that's a function of a position vector. Okay, it's a scalar potential that's a function of a position vector, and we're taking the gradient of it. And what does that mean? It means we're taking the partial derivative of the scalar potential function with respect to x in the x direction, plus the partial derivative of the scalar potential function with respect to y in the y direction, plus the partial derivative of the scalar potential function with respect to z in the z direction. Or in cylindrical coordinates, the gradient of the scalar potential function is going to be the partial derivative of the function with respect to rho in the rho direction, plus 1 over rho plus the partial derivative of phi with respect to phi in the phi direction, plus the partial derivative of the scalar potential function with respect to z in the z direction. And then you can do it in spherical coordinates as well. And this is all happy. This is nothing to be afraid of. Just keep in mind the general concept that the gradient is the direction, the direction of the gradient is the direction of steepest ascent, and the magnitude of the gradient is the rate of steepest ascent. And this is how it's expressed mathematically. When you think about steepest ascent, the rate of steepest ascent, you should be thinking of a derivative. The derivative obviously is the instantaneous rate of change of a function. In this case, it's not instantaneous with respect to time, it's instantaneous with respect to displacement. So, okay, going back to electrostatics, the electric field due to a single point charge is given by Coulomb's law, which is that the electric field due to a point charge is going to be the charge divided by 4 pi epsilon r squared, where epsilon is the permittivity of the space and r squared is the distance from the charge and in the radial direction. So I have a proposition here. The electric field is a conservative field. That is to say that as you move a charge through this conservative field, the electric potential energy per unit charge, or the voltage, is path independent. It doesn't matter what path you take, the change in the voltage or the change in the electric potential energy per unit charge is independent of the path you choose to take. Here's the proof. So we have this electric field, and we said that if the electric field is the gradient of a scalar potential function, then it is a conservative field. So if phis are electric potential function, then here we are in spherical coordinates taking the gradient of the spherical of the electric potential function, the scalar potential function. And when we resolve that into components and then do some algebra, do a little bit of calculus, yada, 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 we get this equation here, which says that the electric potential function at position R2 minus the electric potential function at position R1 is equal to this expression, Q over 4 pi epsilon times, in parentheses, 1 over R1 minus 1 over R2. And so indeed, this is the voltage between R2 and R1, position R2 and position R1. This is the voltage. That it is a conservative electric field that we're talking about. And we do have a scalar potential function. We do have a voltage between 2 points that's dependent on position only and not dependent on the path taken by a charge that we take from one place to another place. The path doesn't matter. It's a conservative field. There are no variations of the scalar potential function in respect to theta or phi. It's just the electric field due to a point charge is varies with respect to the distance from the point charge, not with respect to which direction you're moving in, but how far you are from the point charge. So to pick a reference point, it's convenient to pick a point at infinity. And then when we let R2 go to infinity, then we can drop the one term and we just get the phi, the electric potential function equals negative Q over 4 pi epsilon R. So we have the scalar potential function whose gradient is equal to an electric field. And so we've proven that the electric field intensity due to a point charge at the origin is indeed a conservative vector field. And this expression for students of electrostatics will be very familiar, as I've already indicated in this video here. This is a voltage. Okay, so the voltage is the line integral of Q over 4 pi epsilon R squared, AR.dr. And as we go through the calculus, we get this expression over here, which I showed you before. And so the voltage is that scalar potential function. So the electric field, it's the negative of it. So the electric field is the negative gradient of the voltage. The voltage is the scalar potential function. The electric field is the conservative field that you get by taking the negative gradient of the voltage. Since it's a conservative field that's path independent, it follows immediately that if you take a closed path, if you take a charge around in a closed path so that your final position is the same position as your ending position, then the net change in the voltage will be 0. And that's true for all conservative path independent fields. The closed line integral of the electric field as you traverse around some path and you start and end at the same place, then the voltage difference between your final position and your ending position will be 0, because the voltage is a function of position. It's an electric potential function. And this is just another way of stating Kirchhoff's voltage law, that the summation, and you might remember from circuit theory, that the summation of the voltages around a loop equals 0. So to recap, the electric field established by a point charge at the origin is a conservative vector field. The line integral of any conservative vector field is path independent. A conservative vector field is a gradient field of some scalar potential function. The gradient of a scalar potential function at any particular location is the direction and rate of steepest ascent. And the electric field established by a point charge at the origin is oriented in the direction of steepest descent. So a positive electric charge establishes an electric field oriented radially outward, and the electric field intensity drops off according to 1 over r squared. The same positive electric charge establishes concentric circular equipotential contours. So if you have a point charge, you're going to have equipotential contours that are circular, dropping off as 1 over r squared as you get further and further from the point charge. The voltage drops off according to 1 over r. The field drops off according to 1 over r squared. The del operator transforms the scalar potential function into a conservative vector field. It's a linear transformation. Since it's linear, if you have more than one charge, you can apply the principle of superposition. And so whenever an electric field is established by electric charges alone, the electric field will be a conservative electric field, and the closed line integral of any conservative field is 0. Okay, now all this changes when you start introducing time-varying magnetic fields. In that case, then the electric field is no longer a conservative field, and this whole idea of voltage kind of sort of goes away during transient conditions or during time varying conditions. When you have time varying magnetic fields, then energy is sloshing between the electric field and magnetic field. So the electric field is no longer a conservative vector field. Taken together, the energy is still always conserved. So if energy is if you're losing energy from the electric field, you're going to lose it to the magnetic field. Or if you're losing energy from magnetic field, you're going to lose it to the electric field. And this is where you get into Maxwell's equations and, changing magnetic field induces an electric field, and changing electric field induces a magnetic field. But right now, we're not talking about time varying magnetic fields. We're just talking about electrostatics when there's no time varying magnetic fields to deal with. So the electric field is a conservative vector field, and the idea of voltage applies. So an example, I showed in a previous video some electrostatic simulations. Here we just have a charge, and we see these equipotential contours. At this point, we're at 12.7 volts. Out here, we're at 6 volts. Out here, we're at 4.5 volts. Out here, we're at 3.1 volts. Out here, 2.2 volts. Out here, 1.6 volts. And the further and further and further away you get, the lower your electric potential or your voltage is. And you can see the fields. The fields are very strong here when you're close to the charge. And as you get further away, the fields drop off according to 1 over R squared. Here's a case where you have a positive charge here and a negative charge here. So in this case, you get very high voltages when you get close to the positive charge. When you're close to the negative charge, you have very negative voltages. Here we have the 0 voltage, but you can see these equipotential contours here. Again, notice here that the field, the electric field at a contour is always going to be oriented perpendicular to the contour, because the electric field is the negative gradient of the voltage. And notice that it's oriented directed away from the positive charge, from the place of higher potential, toward the negative charge, the place of lower potential. So the electric field is a negative gradient of the voltage or the scalar potential function. You can see that the charge, the field is always going to be perpendicular to the contour. And here I just did another example here, another simulation. Here we have 3 negative charges packed closely together and 1 positive charge here. And you see how that affects the equipotential contours. But you still have these equipotential contours. Notice also here that when the equipotential contours are close together, the field levels are very high. When the equipotential contours get further and further apart, the field levels are relatively low. And of course, the further and further away you get from the charges, the lower the field level. But in between here, you have the superposition of the field due to this charge oriented this way, downward. And then you have the field due to these charges, which are oriented downward too, superimposed. So you have these really tightly bunched contours. This is where you might say you have a very steep, if you're going from the negative contours to the positive contours, you have a very steep ascent in this part here, which is why the field is so strong at this part, at that position. For further reading or further video watching, you got some resources here. This particular video is a great video on conservative fields, gradients, and gradients of scalar potential functions and path independence. A couple other articles here. Of course, this simulation tool I got from this website here from Colorado. Great tool for performing electrostatic simulations. That's all that I have for today. Hope you enjoyed it. Hope you learned something. Let me know if you have any comments or questions, and hope you have a good one. Take care.